Our next speaker is Matthias Güdemann, who is Senior Research Engineer at DiffBlue and holds a PhD in Formal Safety Analysis. After a postdoctorate at INRA in Grenoble, he joins Sisteral, a company specialised in formal verification of software for autonomous metros. In 2016, he joined DiffBlue, where he works in the area of automated test generation and model checking for software and hardware. Over to you, Matthias.
Okay, so thank you. It's a pleasure to be able to present the joint work with my colleagues here at the conference. My colleagues Eugene Goldberg, Daniel Kröning, the founder of DiffBlue, and Rashdeep Mukherjee, who has now joined Cadence in the meantime. So the technical title is Efficient Verification of Multi-Property Designs. The working title we chose to have something to remember is actually the benefit of wrong assumptions, and I hope to be able to explain to you how potentially wrong assumptions can be useful in hardware verification. So the motivation for our work is that we saw that in hardware verification, a lot of work gets into developing the most efficient method to verify a hardware design that has a single property verification. So many of the verification approaches consider one single output, one single safety properties, and try to verify it as efficient as possible. This is very good, and it's also successful, has been shown to be successful. But what we saw in our work on the model checker EVMC is that very often designs actually do have a lot of properties. Whatever number you can give, in theory, there's no limit, but thousands of properties is very often to be seen. There's also the case, actually the reverse, so to say, where we have a single property, but a very hard one. And that single property is actually the conjunction of several easier properties. So if we break it down into easier properties, it might actually in total be easier to prove those than the original single one. And this is why we actually decided to do some research in the area of trying to get a multiple property design verified as efficient as possible. To come to a little bit more formal definition of the problem at hand. So we talk about sequential circuit verification of invariants, so-called safety properties. So what we have, a sequential circuit, is a model of a hardware design where we have inputs, we have outputs. In general, the outputs, or a subset of the outputs, actually corresponds to the safety properties. And the circuit has an internal state, and at every time step there is a new internal state is calculated from the current state and the current inputs, and new outputs are actually generated. So it starts in some initial state. There's either one or there can be several, and then evolves over time. And what we actually want to know is that in any possible state that is reachable from one of the initial states, we want to know whether every property PI is true. And we consider hardware design incorrect if it is possible to find an input sequence that actually where actually one of the outputs, one of the properties becomes false. Now we are aware that sometimes it makes sense to have a model where it is actually the intent to have a false property, because model checkers actually do compute a counterexample in the case of a false property, and then we can use that to actually calculate a witness that tells us how we can get to that state. But in this paper, we are concerned with properties that should actually hold, and we can also deal with the other type, and this is described in our paper, which I will provide a link later on. So our main question that we are concerned with is actually how many of failed properties do you actually want to find, or do we need to find in order to fix the hardware design? Because the goal is to have a correct design, all properties should be validated. Of course, the straightforward approach is, well, straightforward. We actually want to calculate every failed property PI. And that actually makes limited sense. The observation that we made is actually that the same bug might actually break several properties for the same reason. And this is actually a problem because calculating the counterexample, so showing that a property actually fails, often requires a lot of time, in particular if the counterexample is steep, which means that the counterexample needs a long sequence of states in succession to actually reach the state that is non-desired. So we propose another approach we call a more practical approach that we hope it will become. Instead of finding all properties that fail, we want to find the hopefully smallest subset of properties that fail, which actually do cause the other properties to fail in a global sense. And we call that identifying bugs, or the debugging set. So the debugging set will contain the smallest number of properties that we have to fix in order to make our hardware design correct. This fits into this comparison between joint and separate verification. So joint verification, we call the check of an aggregate property. So if we have multiple properties in a design, we can actually conjoin them together to a property P, the whole property, and actually check whether that property P holds. And if it holds, then we can be sure that each of the sub-properties does hold. This approach can, for example, in a K-induction model checker, this approach can actually be beneficial, but for things like IC3 or the more advanced one that we have now, it's actually often not the case that this is the more beneficial formalization of the problem. On the other side, we do have separate verification where we actually prove each property separately, with the idea that as a property Pi is weaker than the property P, it should be easier to prove. It's always difficult to tell, but it should be, and we hope so, and very often it also is. The reason is actually for that several properties can have different proofs. So effectively, if you have an aggregate property and we want to want to prove each of the properties, then we have to search through many different areas of the state space to actually find the proof. If we have a separate property, then we actually don't only have to search in one area, and in particular with a proof method like IC3, which gives us invariants that also hold, so additional properties that we know are true, we can actually reuse them to prove another property. So in that case, separate verification can actually be quite efficient to do. So what we built is, we call it just assume verification. It is an instance of separate verification. So we look at one property at a time, but with a twist. And the twist here is that we verify a property Pi under the assumption that all the other properties hold. And this is crucial here to see that, well, to accept that this assumption is not global. So we don't assume simply all the others and then try to prove it, because that could lead to circular reasoning. But what happens in this proof method is that we look at a set of traces starting in the initial state, a sequence of n states that are connected via the transition relation, and then we try to make the step to the n plus first state. And we assume all the properties did hold on the states that we have seen up to n, but then for the step we actually do not assume them, but we try to prove that our property is still holds as when we actually try to prolong this state sequence. And the proof for this is in the paper, and we can actually prevent circular reasoning because the assumption is not global. We don't actually have to use a justification for the assumption. Well, the justification is actually the proof in the paper, and this is why we named it just assume verification. So to give you an idea of how that looks, and hopefully a graphical explanation that it is also something sensible to do, we discern between local and global proofs. So a global proof is actually proving a property without actually looking at the other properties. So if, for example, we want to prove Pi globally, which is represented here, so the blue circle are all the states that respect Pi. S1 is an initial state, S2 is a successor, so S1, S2, etc. up to Sn is a sequence of states starting an initial state that all respect Pi, but then there's actually a state Sn plus 1, which is outside Pi, which does not respect Pi, so Pi is actually not invariant for the system. In the global proof, when we don't look at the other properties, we actually try to find a counterexample where all the initial states, Sn, S1 to Sn, are actually Pi states that respect the property Pi, and then Sn plus 1 is a not Pi state. So this is what we have for a global proof. For a local proof, we actually do have, it's slightly different. So what we see here is we have this yellow circle, which represents all the states that respect P, and not just Pi, but also all the other properties that we want to prove. So we see that the initial sequence S1 to Sn actually is completely within Pi, and then the step Sn plus 1 is actually outside Pi. And so to prove it locally, we actually only look for counterexamples where the initial sequence actually lies in P, and only the last step brings us outside of Pi. So this is the big difference here is Pi states are the initial states in the first one, in the global proof, and P states in the second one. And what we see here, which is the intention of drawing it like that, is actually that the set of states in P is actually smaller than the set of states in Pi, and therefore it should be easier to find a proof, to find a counterexample that way. Now, there is, of course, a relation between global and local proof, as it would not make much sense to use it. And the relation is as follows. So if Pi does hold globally, then it also holds locally. This is easy to see, as if we have something that does hold without any additional assumption, then it will actually also hold when we add other assumptions to it, because we can just constrain it even further. The other way around is, of course, not true. So if it holds locally instead of globally, then it might, of course, also hold globally, but it could also be that it doesn't. But if it holds locally but not globally, that actually does mean that every counterexample that does break the property Pi does have to break another property Pm from the aggregate property before. And this is drawn here. So we see the blue circle is all the states that respect Pi, the yellow circle, all the states that respect P. And then we see that when Pi holds locally, then we can actually find, before we get to the state Sn plus 1, which breaks Pi, we will find a state Sk, which actually breaks P. In particular, it will break one of the other properties Pm, which makes up P. And so here, Sk is a Pi state and a not P state, and it will break some other property before, and it's exactly that property that we call the cause of failure of Pi. We think this is an advantage to use local proofs because of, in particular, well, this is almost the same here, that we have proving Pi globally or locally, but the difference is here that we look at not P states in a global proof and not Pi states in a local proof. And there are less not Pi states than there are not P states. So reducing the search space will actually lead us to finding quicker counterexamples. And in addition, we also have to find less counterexamples than with a completely separate verification. Now, if Pi actually does hold locally, then we can not really conclude, but we can be sure, almost be sure, that it will not be a bug identifying property, in particular not at that state now. If it fails locally, it is a bug identifying property, meaning that we should fix that property before we actually rerun our analysis again to find either more properties that actually cause a failure, or we can conclude that the design is correct. And we actually know, again, the proof is in the paper, if the overall property P does fail, then we can be sure that at least one of the Pi will actually fail locally. And if at least one fails locally, then it will also fail globally. So we can be sure that we find one of those if the global property fails. So to show a more hands-on example, still a small toy example to fit on the slide, but something which at least looks realistic. It is taken from a system Verilog program, which is one of the input languages accepted by eBMC. It models a counter starting at 0 and incrementing by 1 each time until either we do have a reset, until we have a reset, and we will initialize with 0. And the idea is to have the reset either when we have reached the reset value or when there is actually a reset request, which is an external signal. For this, we have two properties. One property says the request is always true, and the other property is that we will never exceed the reset value. So whenever we actually reach the reset value, we'll reset and we'll never exceed it and never see something bigger in the value register than it is in the reset value. Of course, it's obvious to see that the first one is false. For the second one, it's maybe a little bit less obvious, but both properties actually do fail globally. Now, to show what difference it makes when we use our local proofs, when we try to prove both locally, that is, we prove one under the assumption of the other, we actually do see that only P1 fails locally, P2 actually holds locally. So in our notion, that means that P2 actually is the bug that we have to fix before we should have another look at the second property. And the bug here, I mean, it's written in red, and it's quite obvious that the bug here is actually that we have a conjunction. So we actually define the reset as either being in a reset state and having a request, which is very unlikely. So this actually should be a disjunction instead of a conjunction. So in this case, but what we see is that instead of having to compute two counterexamples, it's sufficient to compute a single counterexample. In particular, we do see that if we have a very large reset value, the counterexample trace that we would have to compute for 2, so to prove that it fails globally, can actually be very, very long. So effectively for such a system, we can make it arbitrarily long. It's of course not a super realistic one, but even in realistic systems, we can have very long counterexample traces. So the just assume approach in general works as follows. We do check, very similar to a separate verification, each property locally, under the assumption that when we do the step from n to n1, so in IC3 we try to prove the time frame n+1, we assume that the other properties had been true before. Not global assumption, but like a local assumption for all states that we have seen before. If every PI actually holds locally, then we can conclude that the global property holds. Again, the proof you will find in our paper. Otherwise, we actually have a set of those properties that we have to fix before we can actually prove the correctness of our design. And then this is where actually our notion from using the benefit of wrong assumptions comes from, that even if a property PM does not hold globally, even if it's not invariant, then assuming it for the prefix of a trace, for the prefix of the timeframes, it can actually be beneficial to use, because we actually do drop traces where the PM fails before PI, and therefore reduce the search base for a verification method. We have implemented that method on top of EBMC. We added the IC3 algorithm to it in a special version for DiffBlue, which can actually treat problems with multiple properties and implements the just assume verification. There's more technical detail how it's done today, but this will be integrated completely into EBMC very likely soon. One thing that we had a look at but have not solved completely is exploiting the fact that multiple properties might be of different difficulty. In particular, it might make sense to prove easy properties first to get rid of them, but also to learn from them. When you do have a proof method like IC3, you will see that every successful proof gives you additional inductive invariance, which can actually be reused in order to prove other properties with them. And therefore, proving all simple properties first is very beneficial when you can then use the over approximations that are calculated by IC3 to prove the more difficult ones, because effectively you start from an already advanced internal state of the proof engine. But for now, we just verified the properties of a design in the exact order that they were listed in the original description. We come now to the experimental section, where we did a comparison between our verification approach and joint verification. We saw that joint verification is often less robust than the just assume verification. Well, already less robust than separate verification, but in particular just assume verification, which is due to the fact that proving an aggregate property might fail simply because of just a few very hard properties, even if the others are very simple. And properties might be very hard because you have to the properties might depend on very different local behavior, which is not very well reflected in an aggregate global property. There are approaches that try to solve that via clustering, reordering of the properties, etc. But for our approach, it doesn't matter. It could have something like that on top, but for currently, we don't do it. There are other approaches in the paper. There's some discussion of related work to that. in order to evaluate our approach in comparison to ABC, developed in Berkeley, a very high performance implementation of IC3 under the name of PER, property-directed reachability analysis. We used the hardware model checking contest benchmarks from 2013, not because we can't handle the current ones, but because this was the last time there was actually a multi-property track. Now there's only single track, and this is, as far as I know, not done because there's no interest in that. It's done because it's very difficult to rank in a fair manner tools that do the multiple property verification. What we did, we chose 8 designs that are correct and 8 designs where we actually do have faulty properties in it. So some properties fail. So what we see here is the results for the failed property designs. So we have the names of that as they appear in the hardware model checking contest files, the number of state bits, the number of properties. So this is the description of the designs. And then here we have the results of joint verification, one time for ABC and one time for our implementation. And then the results for just assume verification for our implementation. So what we see is here is first the number of properties that are false. And then in parentheses, the number of properties that are considered to be true. And this is the time budget that we allotted to the verification engine. And when we see a little star behind the result, then that actually means that all the properties that were in the system have actually been treated by the verification method. So we get an answer for each of the property, either true or false. Now what we see that ABC didn't solve all. In general, it was a bit faster than IC3DB, not always, but most of the time it was, and it's quite efficient. When we look at the just assume verification, we see that the time limit was much lower, and that it actually gave us a result in almost each case, just one case where we did not get a result, but in general it was much faster than the other approaches and gave us more results. It is a bit comparing apples to oranges because the result is of course something different. So when something is true here, it's locally true and not necessarily globally true. But again, with our reasoning, it makes sense to analyze this fact. Now for the correct designs, again, we have the name, number of state bits, and the number of properties. Joint verification with ABC and with our IC3 implementation, and the just assume verification with our approach. We see that most of the time ABC is faster in joint verification than IC3 in our implementation. When we compare our implementation for just assume verification and joint verification, we see that it's more or less evened out. So what's set in bold is actually when it's faster. So 4 out of 8 times the just assume verification is faster, and 4 out of 8 times the other one is actually faster. So this is a little bit inconclusive, but we can see that at least just assume verification is not worse in that sense if you compare it with the same implementation. And the just assume verification, as I said, is independent of the actual implementation and could also be integrated in the ABC, for example. So to conclude my talk, so what I did, I introduced the just assume verification as a special case of separate verification. It is currently purely semantic. We could, and it might make sense to add more knowledge about the structure of the problem at hand to it, which might make the verification of some designs even more efficient. This had not been done. This might be something for future work for us. There are approaches also, for example, implemented at ABC that actually analyze the structure, so that could also be used as a pre-processing for some of the models. The assumptions do not need any justifications. They are still correct in the sense that I presented. Again, to state that it's not a global assumption, but an assumption on the when we do a time frame step from n to n+1, we assume the correctness of the others for up to n, and then try to prove for the problem, for the property at hand, for the step from n to n+1. The big advantage is that we will have to calculate less counterexamples, because there will be other properties that are actually locally true, which are globally false. So no counterexamples for them to calculate, which can be a lot faster, as we have seen in the example. And we also, to construct a counterexample, we actually have to search through less state space, which also makes it more efficient, actually. And what we've seen, so finally, even if we actually look at correct designs where our approach does not really give an advantage, it's still competitive. And as we use IC3, we could actually make it maybe even more efficient when we would reuse the inductive invariants that are found. So if you are interested in that, I want to have a look in more detail, in particular in the proof, there is an extended version of our paper at the Design Automation and Testing Conference in Europe this year, 2018, where it won the Best Paper Award. This is the extended version with more with the proofs completed. Or feel free to contact me at Matthias Güdemann at diffblue.com. So thanks a lot.